Hopefully you already think perception is interesting and amazing. Why else would you be listening to me? With this first demonstration, I want to make clear, however, just how impressive your perception is. I'm going to show you a series of simple object pictures. They're pictures that you haven't seen before, and I'm going to show them to you in rapid succession. Perception researchers call this Rapid Serial Visual Presentation, or RSVP for short. This sequence of images is being presented at a rate of about 10 per second, about 100 milliseconds per image. As you view these objects, you might notice first off that you can recognize them, even with this very brief viewing time for each one. If I stopped the RSVP images here, and then asked you to write down all of the objects you remember, you might be able to write out a list of many of them, but you probably wouldn't get them all. But that's a harder task than the one I want you to do right now. To write that list of objects out, you'd have to not only perceive and recognize the objects, but you'd have to encode them in your memory and then successfully retrieve those names as you wrote down what you'd seen. For the moment, all I want to establish is that you can do the recognition part of this task. That in a matter of 100 milliseconds, you can perceive the pattern of light in the image and associate it with a verbal label that you already have stored in your mind. To do this, I'll give you a probe word and ask you to respond when you see the object picture that goes with it. Let's try car. So watch the images and imagine pressing a response button as soon as you see a car. Okay, go ahead and do that now. Let's try another one. This time, press your imaginary button when you see a computer. If you're like most people, you'll find that you can do this rather easily. It will still work even if I give you a broad category name. So this time, press your button whenever you see a vehicle. This time, press the button when you see something you would eat. I can even do it with an object feature. Press the button this time when you see something that flies. You're able to do all of these tasks with only 100 milliseconds of viewing time. And you can do it pretty easily at that. I just want to stop for a moment and point out how amazing this is. You can do this with these very simple images. Images that lack all of the fine texture, color, and detail that you would encounter if you were looking at the actual objects in real life. Also, you've never seen these pictures before today. Particularly on the first run-through, your visual system was doing all of its processing inside this tiny 100 millisecond window, working from scratch with a brand new stimulus. Let's try this RSVP task again, this time with the objects being presented faster, at a rate of 20 objects per second. So only 50 milliseconds per picture this time. So now I want you to hit your imaginary button when you see a musical instrument. Now hit the button if you see something you might eat for breakfast. Your visual system is not infinitely fast. It's still possible to show a stimulus that's too fast for you to recognize something. But this is really fast. As long as you have about 100 milliseconds, this task is easy. As easy as this is for you, we have encountered no other information processing system capable of this other than the human brain. No supercomputer, no other animals, nothing in the entire universe of scientific exploration. The human brain, your human brain, is just flat amazingly good at this task. Auditory perception is just as precise, rapid, and generally amazing as your vision. Consider the seemingly simple task of listening to someone talk. As you're listening to me right now, literally dozens of sound units are reaching your ears every second. You hear the individual words that I'm saying, but they're embedded in a continuous stream of sound that's pretty amazingly complex. If you've ever listened to someone speaking a language that you don't know, it will be easier to be aware of this continuous aspect of speech. Here's a recording of someone speaking Aymara. This is a Native American language spoken by about 1 million people who live in western Bolivia. If you do speak Aymara, you'll just have to trust me on the next few things I say.
Atas alun take to kat at negosyo taki itak pas taki ko maran at sila nakapuri ko panaga kan wali chaman wali frisan na nakataki na nakapara ko atin tipta apoy jurapta panaga ko apoy ta para kitilat.
Notice that this recording sounds like a continuous stream of unbroken sound. It seems like there are no pauses between the words as there are in English, right? Actually, there are no pauses in between the words, either in this recording or in the English speech that you're hearing right now. This lack of pauses in between words is true for all languages that humans commonly use. When you listen to me, you hear individual words, but there are no auditory spaces in between them. If I talk with gaps in between words, it sounds very stilted, to say the least. Your auditory system identifies the words in the sound patterns so fast and well that it doesn't need those pauses. Consider even the sounds ba and pa. I am swinging the bat is very different from swinging my friend Pat. Handing you a pill and a bill are totally different. How do you know which one I'm saying? For both sounds, you start by constricting your vocal tract and building up pressure behind your lips. You then release that pressure and exhale slightly. As you do, you engage your vocal cords and make a vowel sound. You do the same thing with both sounds, ba and pa. How do you make one sound or the other? The only difference, it turns out, is a slight change in the timing of the onset of your vocal cords, the so-called voice onset time. If you start the voicing at the same time you release that built-up pressure from behind your lips, you hear ba. If you wait about 15 extra milliseconds, it comes out as pa. Just 15 extra milliseconds, a little extra time. Short voice onset time ba, just a tiny delay and you get pa. These very fine distinctions, on the order of a few milliseconds, are made by your auditory system dozens of times a second in order to understand speech. Computers have gotten better at parsing speech, but they aren't nearly as good as people. I often call the automatic ticket agent when I schedule airline flights and train tickets. And under ideal, quiet conditions, if I speak slowly and clearly, this can work out okay. But if there's a noisy connection, or if I'm at the noisy airport and in a hurry, I find myself really wishing for a much more proficient human operator. Humans, even children, are still far better at processing verbal speech than even the best of these artificial systems. As with vision, hearing feels so easy, so effortless, that most people assume there must not be much to it. But when we try to duplicate what our brain is doing, we quickly realize just how amazing perception is. Our sense of touch is amazing too. We think of touch as registering pressure information through the skin, but much of the really useful information comes through vibration. If I drag my fingers across a smooth, hard surface, there's one pattern of vibration produced at my fingertips. If I drag it across a rough surface, another pattern results. Our brain is masterful at interpreting these patterns. If you reach into a bag stuffed with clothing, you'll be able to pick out that particular old flannel shirt, or the jeans, or the spandex, all of it based on just a few milliseconds of vibration information delivered through the fingers. In this course, as we explore the human senses, we'll see this sort of thing over and over again. Our sensory systems gather a tremendous amount of information very, very quickly. Even more impressively, we almost instantly relate this incoming information to other things that we already know. Your sensory systems also take into account information about your immediate context in a very flexible fashion. For instance, if you're in a grocery store looking for bananas, your attention will become very attuned to the color yellow. As you drive, your eyes and ears become attuned to the information that you need to drive, and less sensitive to other sources of information that aren't relevant. This massive, complex, flexible, automatic, interactive, accurate perception process is going on all the time, every moment that you're awake, and to some extent even when you aren't. Perception is amazing. So how does human perception accomplish all of this? How does our brain outperform everything else in the known universe in terms of sensory processing? A full answer to this question is certainly beyond the scope of this first lecture, but one of the key tricks that our senses use is to be inherently inferential. Our brain makes educated guesses about the state of the world around us based on our sensory inputs. And it's those educated guesses that you perceive. Not the sensory inputs themselves, but the results of our perceptual inferences. It's precisely because our senses are so good at making those inferences, so perceptually intelligent, that our perception is so amazing. Now, most people think of inferences as cognitive operations, the sort of thing we perform in classes on logic. So if John is taller than Betty, and Mark is shorter than Betty, then we can infer that John must be taller than Mark, right? The inferences I'm talking about here are related to this, but they occur automatically and outside of our conscious awareness. They occur very quickly and are based on some extremely complex relationships between different information sources. And they don't happen only at a higher cognitive level. The inferences start right at the level of the sensory organs themselves. Let's consider one class of inferential process that happens in your retina. For this demonstration, you'll need a pen and a piece of paper. Almost any piece of paper will do. I usually use an 8.5 by 11 sheet folded in half. What you should do here is make two small X's, maybe about 4 inches apart from one another. You want to make them relatively small, maybe about 1/4 inch at the most apiece. What you should then do is set your pen down, hold the piece of paper with the 2 X's in your right hand, and hold it out at arm's length. With your left hand, cover your left eye. Now I want you to fixate on the X on the left and very slowly bring it towards yourself. Now, as you're doing this, you want to make sure you keep your right eye looking directly at the X on the left, but pay attention to the X on the right. As you bring the X's slowly closer to you, somewhere around there, the X on the right will vanish. You can do that a few times just to make sure to yourself that the X has vanished, or rather, the X is still there, but it really does seem to vanish when you have it at just the right position. The X is still there, of course. You know that. What's happened is that the X has passed into the blind spot on the back of your right eye. This blind spot is caused by a characteristic of the anatomy of the human eye, of your eyes. Light passes through the pupil and the lens of the eye and projects onto the retina, which covers the back interior surface of the eyeball. The retina itself consists of a dense mosaic of light-sensitive neurons called photoreceptors. About 1 million neuronal connectors, called axons, extend from each particular location on the retina to the optic nerve, located in a particular spot a few millimeters away from the center of the retina. The optic nerve is a bundle of about 1 million neurons that extends from each eye back into the head and the rest of the brain. At that location on the retina, where the optic nerve begins, where the 1 million axons all come together, they pile up on top of one another and create a blind spot, a location on the back of your eye where you are blind. There's a blind spot on each of your eyes where you just can't see. Now, as you look around the world, you don't notice these black holes in your visual fields. Even when you cover one eye, you still don't see it. Even when the X vanished into the blind spot, you probably noticed that it didn't move into some sort of a black hole. It moved into a space that was the same color as the paper. In essence, your visual system makes an educated guess about what's in that blind spot, an inference based on the nearby areas of the retina. And it's that inference that you perceive. You're perceiving something that is not present in the visual input. You're perceiving the result of an inference. Let's go back to our X's again. This time, what I want you to do is, around the X that you're going to make vanish, draw a grid of vertical and horizontal lines. You might want to stop the video to give yourself a chance to draw that grid. It's important, it doesn't need to be perfectly straight. It's important that it be big enough that it extends beyond where the blind spot is located. Once you've drawn that grid, make that X vanish again. So again, you want to hold the piece of paper out at arm's length in your right hand, cover your left eye with your left hand, fixate the X on the left, and slowly bring it toward yourself. At just the right position, you will notice the X on the right vanish. Now what I want you to pay attention to here, after you've made that X vanish, is what's in the blind spot. What's located where that X used to be before it disappeared. Assuming that all of this has worked the right way, you should see a blind spot filled with that grid texture. Based on the texture surrounding the blind spot, your visual system infers that the texture is in the area of the blind spot as well. And again, it's that inference, or rather the result of that inference, that you perceive. This inferential process shows up throughout the visual system, and indeed in the other senses as well. And it's a good thing that it does. These optic nerve regions aren't the only blind spots. If you've ever taken a flash photo of someone in a relatively dim room, you've probably noticed the red eye phenomenon. People's eyes seem to glow red in flash pictures because their retinas reflect the light of the camera's flash bulb. What you see at the red spots in a red eye photo is actually a small image of the backs of the eyes, small images of the retinas. If you were to zoom all the way in on one of those red spots, you'd be able to see a detailed image of the structure of the human retina. Among the most striking features of the retina is the dense network of veins and arteries that supply the cells there in the retina with oxygen and fuel. These blood vessels are essential to the survival and function of these retinal cells, but they also do something else. They block the light. They prevent it from reaching the light-sensitive layers of cells on the retina. Every place where you see a retinal vein is another place where the eye is blind. It's as if we walk through the world looking through a lacy latticework of these veins, yet we're never aware of them. Our brain fills in all of these tiny blind regions in the same way that it fills in the large blind spots associated with the optic nerves. This filling in process works so well that some degenerative vision disorders can go undetected for years. Macular degeneration results in a slow reduction in the cells near the center of your visual field. Eventually, a patient with this disorder will notice a loss of the ability to read or recognize faces, but not until the disease has progressed very, very far. Our brain does such a good job of filling in missing sensory input that we just don't notice it. Similarly, retinitis pigmentosa, a disorder in which peripheral vision deteriorates, will often go undetected for years unless you visit a doctor and undergo testing. It's a good idea to make sure you visit your eye doctor regularly. The earlier these types of problems are detected, the more can be done to slow or stop their progress.